everyone. It's my honor and pleasure to welcome here our colleague Jana Strakova. Jana is going to tell us what's new with UDPipe, so the floor is yours.
Hello and welcome. I'm Jana Strakova, and this is joint work with Milan Straka, who is teaching right now, so he cannot be here. So I apologize for him, and I will speak the whole time. So this is about UDPipe, which I guess all of you know. It's a pipeline for morphology and lemmatization and syntax dependency parsing. And just to quickly get us on the same page, I'm going to very quickly show where we are now with the development of UDPipe. So it all started in 2014, when we showed Morphorita and NameTag, morphology and lemmatization tool and named entity recognition tool at ACL demo. And in 2015 we created Parsito, which was a dependency parsing tool. And in 2016 we joined them together, and this was the first version of UDPipe. We tried to, or we did, participate in Convo 2017 share task, which was morphology, lemmatization, and dependency parsing from tokens. From the raw text, so you didn't even know where the tokens are. And the UDPipe was used as a baseline system, and it ended up 13th, so there were some systems which were even below this baseline system, and our own contribution was 8th. Last year, we again tried to compete in the shared task. The task was the same, so dependency parsing from raw sentences with a new prototype, UDPipe 2.0, in which we replaced the core with TensorFlow. So we started using TensorFlow, and UDPipe was one of the 3 winners. And now I get to this year's work, which will be the core of this talk. So this year, the talk will be a compilation, or will be consisted of 5 papers. One of them is where we took the UDPipe 2.0 architecture and added contextual embeddings to it. We did this experiment for 54 languages where there was enough data to do this. Sadly, the paper got rejected from EMNLP. The reason being we didn't ask any scientific questions. It was just evaluation, although the results were state-of-the-art, but still not a really scientific paper, more an evaluation paper. So the Czech portion of the experiments was presented at Text, Speech and Dialogue 2019, and you will see some visualization of these experiments. Then this year we also participated in Sigmar Fund 2019 share task with UDPipe. This was a workshop collocated with ACL, and again we used the similar architecture, UDPipe with contextual word embeddings, but only the morphological part of it, because the task was only morphology and lemmatization. Now the very interesting part was we tried to do semantic parsing, which we never did before, so it was a huge challenge for us, and we didn't have any expertise in it. So we tried the shared task called Meaning Representation Parsing, and after fixing a bug, we ended up 3rd, and I will spend a lot of time about this because it was quite complicated and it was a lot of fun and frustration too, so we'll get to it. And we also had some nice results in nested named entity recognition. This was motivated by the fact that Czech named entity recognition, Czech named entity corpus contains nested entities. So we wanted to have a nice parser or recognizer to recognize nested entities, and so we had some good results. And a nice surprise for the linguistic audience here, we also had, we looked at the errors in Czech, and we published the errors in, or the errors are going to be published, the interesting cases in Slova Slovesnost, and that will be part of this talk too in the end. So This talk is going to be the black part. Okay, so first a reminder of the UDPipe 2.0 architecture. The task was called multilingual parsing from raw text to universal dependencies. So the input is raw text, you don't know anything about it, and the output is ideally dependency tree and all kind of morphological analysis. So the architecture is kind of pretty standard now, but it was interesting a year ago. The start is the red part here, that's the encoder. If we have a word, input word, we use pre-trained embeddings, trained embeddings, and character level word embeddings. Contextual embeddings were not known a year ago. Maybe Elmo was, but we didn't use it. And then once this is encoded, it all goes to shared recurrent neural network layers. They are processed, the inputs are processed with 2 layers of long short-term memory units, and then they go separately to tagger and lemmatizer and to dependency parser. The biofine annotation here is dosat. So this is our architecture in a nutshell, and we will get back to this picture later again when we will change things in it. Okay, the results from back then, last year's competition is this line, the first line. The first part is you have to get the tokens, words and sentences right, then the morphological section and the dependency section. We think that our strength of UDPipe is in lemmatization and morphology, so all through the other shared tasks we will see this pattern that tags and lemmatization are good. Dependency parsing is not like excellent, but we managed to get first in one of the metrics. This one is unlabeled attachment score, this one is labeled attachment score, and this is a combination of labeled attachment score and morphology. So now you see, because we are strong in morphology, so morphological labeled attachment score is promoted by this. Okay, so here's the obvious addition to the architecture, something that everyone would think of when they see BERT published. We add it on the input, so right here we would add frozen Elmo style BERT contextual embeddings without any fine-tuning, because it's computationally expensive, and like adding a frozen embeddings is not so expensive. So we edit these embeddings, and not so surprisingly, or this is not so very new result now, in the fall 2019, the results go up. The thing to contrast here is the fourth, this is from the paper, so I will just highlight the most interesting rows. The fourth row, where we have word embeddings, character level word embeddings, and no BERT, no contextual embeddings, and again, morphological section and dependency parsing section. And the last row of the table, where we have word embeddings, character level word embeddings, and BERT base. This is an average for all 72 UD 2.3 treebanks. So you can see that between these two rows, the results go up. Interestingly, and we see this pattern through all our results, it is less so in morphology, and the gain is much higher, much more prominent in syntax. So we can say, but it is also not a very novel result, but we can say that syntax is better encoded in the BERT embeddings than morphological information, but that's also not so surprising given the way that the BERT are trained. Okay, I also have some nice visualization for Czech, so this will be much better seen on nice colorful graphs. So this is part of speech and lemmas. On the Czech part of universal dependencies, so this is the Czech PDT portion of UD, and that's UDPipe 2.0 plus BERT. So the blue column is the winner of the share task in a check, and the yellow one is the second rank contribution. Ours is the green, without the contextualized embeddings, is the green bar, and with the last one is with bird. So you can see that there are gains, but marginal ones. And the situation is quite different in syntax. So again, the blue and yellow bar are the share task participants. Our contribution is the green one, and adding bird increases our syntax scores very well. Okay, so then we moved to this year. So this year we tried to participate, or we did participate in task 2 of SIGMORPHON 2019 share task. It was called Morphological Analysis and Lemmatization in Context. So what was the task? The task was you get a sentence, they buy, for example, they buy and sell books. It's already tokenized, so no problem here. So you get a tokenized version of the sentence, and the task is to fill in the second column, which would be a lemma, and the fifth column, which is some set of morphological marks or tags. If you wonder, or maybe you don't wonder, but I did wonder what this is, it's a unimorph scheme. It's a derivation of UD. So they take the UD data sets, so they have 66 languages in 107 corpora, and they are tagged with unimorph scheme. Why unimorph scheme is better than what is in UD is for you to read the paper, I don't know. Yeah, theoretical reasons. You're invited to read the paper. For me, it's just a question of modeling. So, we were supposed to fill in these tags. If some were missing, you got points. You got fewer points. So there were four measures in the competition. The first one was lemma accuracy. So the task was you had to get the lemma right exactly as it is. If you had if one character was wrong, no points. Then the second one was lemma Levenstein. That means the distance from the correct from the gold lemma. So some points if you get the lemma partially. Lower is better. Then morphology accuracy. That means you have to get the set of the morphological text, all of them. The order is not important, but you have to get the exact set. And this is a recall and F measure, a combination of recall and precision of the individual tag sets. You see, we were very strong in lemmatization and shared with, so we ended up on the shared first place. The nice thing here is Charles Arland is Dan Kondriatuk, so whom you know maybe, he's Milan's student. So, but he took part in the competition independently of us. So this was nice, and now the semantics. So we decided that it would be fun if we tried to add some semantics to UDPipe. So we enrolled in Meaning Representation Parsing share task. It was a whole new experience for us because we didn't know anything about semantic parsing before, and the task itself was an interesting one. So the goal was data-driven parsing into graph structural representation of sentence meaning in so far in a very vague meaning of these words. So don't imagine any particular formalism behind these words, and we will get to them. So we had, what was the part? There were 5 formally and linguistically different approaches to the meaning representation in graph, and we were supposed to somehow model all of them. All of it was in English. which I personally think was a shame because, yeah, we would like to have more languages, and hopefully next year, when the competition will probably be repeated, there will be German and Czech, hopefully. So yeah, I will quickly go through the formalisms, and since you are much more experienced in theory in semantics, you will see more in them than I did see. So I apologize for any inconsistent and imprecise formulations. So the first data set that we had was delved in bilexical dependencies. I'm going from the simple ones to the most complicated ones. So here is an example sentence. A similar technique is almost impossible to apply to other crops, such as cotton, soybeans, and rice. And here's the tree. Sorry, it's not supposed to be a tree, it's supposed to be generally a graph, because it doesn't have to have a root, and it doesn't have to be connected, and so on, so it's generally some graph. In this framework, the nice thing for people who are trying to parse it is that the nodes in the semantic tree always correspond to some token on the surface. So, yeah, that's a nice thing. There are no added artificial made-up nodes, such as compositions or something else. The graphs don't have to be fully connected, they don't have to be rooted, though there exists a notion for the purpose of the whole shared task, the organizers promoted a notion of a top. Top is something that is important in the graph, and we are supposed to model the tops too. So in this graph, or in this formalism, the top is almost. I don't know why, but this is the official example. Some tokens can be omitted from the semantic graph if they are not meaningful. What's not seen in the graph is that all the nodes may or don't have to have labels and some undefined number of properties, and the same with labels. The labels here remind us of semantic row labels, and that's probably the simplest of the frameworks that we had. Another one was, I would say, a port of Prague style semantics to a simpler set of rules. So we have the same sentence here, and again, the rules are that the nodes have to correspond to meaningful tokens. Again, there are no artificial edit nodes, so we see this is not really a T layer. There's different labeling scheme than we saw before, but it does remind us of the Prague style tagging or treebank. Then predicative is meaningful and is part of the tree and is at top of the tree, so it's very different from this point of view. Almost does not scope the entire graph, it's a modifier, and there are some more differences. Okay, so but now it gets much more complicated. So this is the third framework that we had. Elementary dependency structures. Again, the same sentence. Now it gets a level more complicated because the nodes don't necessarily have to be the exact tokens from the sentence. They can be an arbitrary selection of characters from the sentence. So it could be either a concatenation of words, if you need such a node, or it could even be a divided, for example, in a sentence, he set me up, they would have set and up go into one node, and there's me between. So you could have holes in the, it doesn't have to be a consecutive string of characters. But still a nice thing is that there is a pointer to the underlying sentence, although it's still just characters, and it doesn't have to be the whole word, and it doesn't have to say anything. Another thing is that you see the labels are not lemmas anymore, but they are some dictionary entries. The bad thing is we didn't have the dictionary when we modeled the graph, so we just were supposed to magically find the node labels. Yeah, so I guess I said everything about this framework. So the fourth framework which we had was universal conceptual cognitive annotation. Again, the same sentence. And you see it's something like constituency tree. So all the words are in the leaves. They don't bear much information, and all the information is implied from the labels of the edges. So the information about the semantics is rather in the structure of the tree and in the labels and attributes of the edges than the nodes. So again, a different view on semantic modeling. And finally, I am moving to the most difficult one from the point of parsing, and that's abstract meaning representation. And now the fun part starts. So the nodes don't have to be connected to the underlying sentence at all. They can be just made up to represent something. Also, the labels are from some dictionary. What else? It can be a general graph. It can have re-entrances, so cycles are allowed. And there's an important thing which I wanted to say about this. Oh yes, and when the data set was done, the decision was made that there is, even if the word like cotton, soybean and rice is an existing word in the sentence, so it does correspond to a certain token in the sentence, the link to the token is not annotated in the data. So you get a data set where you have a raw sentence, and then you have a tree, but you have no idea how the tree corresponds to the sentence. So there are papers recently on how to reconstruct this alignment from the tree to the graph to the underlying sentence, but it's a much more difficult task if you don't have any clue. So yeah, so this was the setting of the shared task. To sum up, we had some structurally and formally different linguistic approaches where the nodes correspond to the surface nodes to some level. Artificial nodes like compositions may be added in some frameworks. We don't know anything about the graph structure. Nodes may have labels, mostly lemmas, or some dictionary entries. They may have some undefined number of properties which must be guessed. So for example, for nouns you want to predict case and number, but you don't want to predict the same values for verbs and so on. And this must be modeled. Edges also can have labels and attributes, and there is some undefined number of tops in the graph, the important nodes, so to say. Moreover, the task setting was closed, so only approved data resources were allowed. Some labels were actually named entity labels. Some labels were from treebanks when we didn't have them. And there was a very fuzzy evaluation score, because if you have a very complicated graph like in abstract meaning representation, and then you have another graph that you modeled or you predicted, then finding a graph isomorphism to say how much the graphs correspond and what the F measure should be is a NP complete task. So is a graph isomorphism task. So how it is done is via a S-match algorithm, which is a non-deterministic heuristic search, which gets very, very slow if your graph is very, very bad, because it cannot find the correspondence between your bad graph, which happens in the initial iterations of your training. So yeah, it's difficult. Okay, so our goal was to have, just to forget all these complications and mess, and create one general graph-to-graph model that would somehow model everything, and we wouldn't have to care that in one framework there is such and such dictionary, and another one there is such and such number of labels and so on. So it was supposed to be structurally and formally agnostic, and we wanted to have everything modeled implicitly. So it was supposed to be like general all-purpose machine. So I will go through the architecture in one example. So it's a graph-to-graph model, and what I think is novel, opposed to other graph-to-graph models that I have seen before, is it does parse all of the 5 frameworks, and it is done in this way. If you look at the frameworks from a high-level perspective, you will see that the way in which they differ, the substantial way in which they differ, is exactly the relationship between the graph nodes and the underlying tokens. So we decided that we will jointly model this relationship between the nodes and the tokens as part of the graph. So tokens are actually also nodes of the semantic graph, and the connections from the tokens to the real nodes of the graphs are regular edges. And this allows us to jointly model all the information that you can get from the framework. So the starting configuration here is we have an isolated set of nodes. So we can say this is our starting semantic graph, although very bare one, and it contains tokens, nothing else. We run an encoder, nothing interesting here, some regular embeddings, contextualized embeddings, whatever you can think of, and we get the encoding. And then we iteratively run a set of two set of operations or transformations. One of them is add nodes, and the second one is add edges. So the second step in the first iteration. So the first iteration first runs add nodes operation, and it does so in a layered way. So for all the nodes that we already had, we try to find their neighbors. So if you think about it, the very first step will be that for the tokens, we will find their corresponding nodes. So once they are found, this is the representation in the neural network. Once they are found, we do the second step of operations, still in the first iteration, and that would be finding the corresponding edges between these set of nodes. And if it is necessary, we repeat this all the time until the whole graph is covered. Now, if you think about it and remember the first and second, the most simple frameworks, actually only one iteration is needed to cover the whole Prague-style dependency and Delphi, because they only have nodes that directly correspond to the tokens. So the first iteration of addition of add nodes will create all the nodes, and then the first add edges will create all the edges, and you're done. This is an example from Edessa framework. However, it's selected so that you see that sometimes you have to run a second iteration of these operations. So in the second operation, a second layer is found of nodes, and again at their corresponding edges. One thing we don't know yet whether it was a good idea or not a good idea is that we, as you can see, we always add all the nodes from one layer together as a whole set. That's because adding one after another would be computationally expensive, but by adding them all at once, we lose some information, because there could be a dependency between, not dependency in the form, like relationship or hidden information between, say, these two nodes. But if we add them at once, we don't get this, independently, we don't get this information, we don't model it, we don't cover it. So we are thinking maybe next year somehow we hopefully we'll be able to do this step sequentially, but yeah, we'll see. Okay, so this is our graph and the results. So first the columns. These are the names of the systems. The first part are our systems, and this is the other competitors, the best ones. This is how well we did in finding the important nodes. These are the labels of nodes, mostly lemmas. Properties, you can imagine morphological categories of some kind. Anchors in our graph, anchors are regular edges, but how they are seen in most in the formalisms, these are the connections between graphs, nodes, and tokens, and the regular edges and the attribute of the edges. So, unfortunately, our first submission of the shared task contained a bug, a human bug. Yes, so we ended up on the 6th rank. When we found out the bug, we sent a corrected submission, and then the rank was much better. And the last 3 lines are our ablation post-competition experiments. So the competition submission was 90% training data and 10% for development, and then we tried to use all of the data that we had for training and just a very small portion for the final tuning, but to our unpleasant surprise, we didn't get any better. This is how we would do if we didn't have any contextual embeddings, and finally an ensemble of 5 networks. 3 or 5, I don't know exactly. Much better in numbers, but still third. What's interesting here, I mentioned it before, is that we do well in labels and properties, and that's basically morphology. So yeah, so we had very good results in labels and properties. Not so good in edges. And our worst framework was the one which reminds which looks like constituency trees, because this graph-to-graph generation is not very well suited for creating multiple layers of the constituency trees. But we still wanted to have just one model to rule them all. Okay, so away from semantics, next year maybe some more information. And the nested named entity recognition. First, very briefly, an example what nested named entity recognition is. Clearly, it's quite simple. In the sentence, the Premier of the Western Canadian province of British Columbia, you will see 4 entities in 3 levels deep. Interestingly, the literature on nested named entity recognition is quite scarce. I found a few, like 3 papers last year and units of papers every year, so people tend to avoid this problem for some reason. This is how it is done lately. One of the idea that everyone would come up with, you have some sort of named entity recognizer, and you just iteratively run it and it predicted more and more inner entities until it says I don't want to predict any more entities, and then you finish. So it's from this paper. It's a layered model of Lusatomo with conditional random fields, and you iteratively run it until you have all the entities. Another approach is to somehow try to model the structure of the entities. So you build a structure, some sort of hypergraph, and you model the transition between the entities in some complicated way to capture all the possible entities that could be created in one sentences. And if you model the transition between the states with neural networks, then you get a powerful model of nested entities. And here's our idea. We don't build any structure. We don't iteratively run anything. We just do sequence-to-sequence approach. So the input is, for example, in the US Federal District Court of New Mexico, and the idea is simple enough. We just simply run it through sequence-to-sequence decoder and cleverly wrap up all the entities so that they can be outputted in one long string. There has to be a special tag to say I am done predicting this word and move to another word. So the decoder will just say no entity here, and then it will say I am done, moving to next word. Then it will predict that an entity starts here, again say I am done with this token. And this is an interesting part. It will say I continue with the entity that started before. Then it will say, but there is one word entity at this point, and I am done. And again, moving to next line, and so on, so you get the idea. Now, the question is, can a long, obviously again, the insight is long short-term memory units. Can long short-term memory units remember shallow hierarchy, because this is nested? The answer is yes, because nested entities usually have like 4 or mostly 5 levels of depth. That's not difficult for long short-term memory to remember. So it does work surprisingly well. The results are here. Sorry, it's a tiny font. The first part is related work. And then the corporas we have. In English, the standard corpora for comparing nested entity recognition is AC 2004, 2005. Again, yeah, that's medical protein texts. And Czech named it and corpus. That's not a standard corpus, but it's a Czech one, so we included it. No one knew it at the conference, so yeah, bad luck. And the bottom part is our best model. And the grayish row is our contribution without contextual words embeddings, because we had to compare without them since the previous work didn't have them. So you can see that the gain is quite significant, marked. You can see it without, like with naked eyes. If contextual embeddings, these all kinds of contextual embeddings are added, then we get even more marked results. Okay, the results are pretty nice for flat named entity recognition results. Actually, right now we are holding second place in English, SOTA in NLP progress table for English for CONO 2003 with 93.38, but someone with CNN and something added to it has 93.5, so yeah, but still nice. Okay, and now the linguistic part. We try to look at errors that our system make, and I'm sorry, this will be only in Czech, so I will explain in English, but the examples will be in Czech. So what went wrong? This is our architecture, or we did this this was submitted to Slovo a Slovesnost last year, fall 2018, and it took 1 year to finish the process and wrap it up. So you will see the architecture from last year share task without BERT. This is errors in morphology from PDT, and you know there are 15 positions of the tag, and this is percentage of the percentage of the errors that are contributed to the position. And by far the biggest portion of errors goes to case. How this can be, I will show in the next example. The nice thing is, by looking at the errors, we didn't find any like trivial or stupid errors, like the machine went crazy and hypothesized a stupid mistake. But most of the errors can be attributed to interesting examples, like this one. Ekologické palivo bude vyrábět nový závod Milo Olomouc, největší svého druhu v Evropě. So you see where the problem comes from. It's clearly subject-object problem. It looks the same. It's homonymous, so not so. Yeah, and again. The network probably expects the subject to go to the first place in the sentence and so on. Funny thing, this also is accusative because once the network decided, it decided. Some other problems also come from the fact that you would have to know the exact setting of the situation, like you would have to have an extralinguistic information, like in these cases. Spotřebitel by měl být o hmotnosti nabízených pekárenských výrobků vhodným způsobem informován. Ceník, cenovky, informační tabule. So again, we don't know whether this is a singular or plural. And another one, podle kterého je prodávající povinen spotřebitele řádně informovat. So again, we don't know. And the network doesn't know. Okay, and another type of errors is the case where the word that would disambiguate the tag is too far away, like in this sentence. Jednání s bankami o úpravě podmínek splácení úvěru a získání nových úvěrů, které by umožnily pokračování ve výrobě, se protahuje nad očekávání dlouho. So this is a long sentence with included sentence, and then we have se protahuje, which should be a hint that this is not a plural actually, but it's too far away and the network won't remember or won't see. Okay, now some syntax errors. This is from Universal Dependencies check PDT. The tags are the universal dependency tags, so I hope they are quite self-explanatory. The biggest portion of problems goes to nmod. Nmod is přívlastek neshodný, or it corresponds to přívlastek neshodný, and I will show one example where this is quite clear what happened. So the wrong nmod in this sentence. Posuzování je nyní poměrně přísné, protože míra nezaměstnanosti v Kanadě přesáhla 11%. Now the question is, míra nezaměstnanosti v Kanadě, the network obviously thought that v Kanadě should go to míra, but it should be nezaměstnanosti čeho v Kanadě. So, and this kind of problems we saw quite often. Then some named entity problems. By far the biggest portion of mistakes is the problem with recall. We don't find a lot of named entity recognitions, named entities at all, like in this example. Protest testovala státní zkušebna zemědělských, potravinářských a lesnických strojů pobočka Brno. Test is the name of a magazine. We didn't find it at all, so we said nothing, it's not an entity. And then what you don't see here is that the correct name of the entity is státní zkušebna zemědělských, potravinářských a lesnických strojů pobočka Brno. So it's a very long entity and it's divided by comma. So I would say, so my personal idea is that once the network saw a comma, it's at end of story, we go on. Another one, Rada města Brna doporučila zastupitelstvu, které bude jednat, and the whole entity was supposed to be Rada města Brna. But it only found Brno. And the third one, proti Mělníku působil jistě a nedostal branku, vyjádřil se ke klíčovému postu sportovní manažer. Who knows the Czech named entity corpus? Then you know that there are sport clubs annotated. So this was not supposed to be a city, maybe in another corpus, but in this corpus it was supposed to be a sport club. Okay, so we are at the end now. What's next? What do we hope? What are we working on currently? So this was our 2019 work. We hope to wrap it up nicely, and we hope to go to ACL 2020 or EMNLP 2020 demo. Yeah, that's our plan. How it goes, we'll see. But yeah. And the papers, if you're interested, you're welcome to read any of them. That's all. Thank you.
Now we have time for discussion. So.
Thanks. Nice talk. Nice work. I have a short question about the named entity recognition error, one of the almost last slides that you had there with the státní zkušebna zemědělských, blah, blah, blah. Does the model have any idea about the part of speech?
Yes.
So it sees that it ends with an adjective and there was no further noun.
Yes. So name tag has a morphodata in it, like included, and all our prototypes use some kind of part of speech hint. So either we use morphodata or we just jointly model it. But in any case, at the time when this is decided, there is part of speech hint. So it's very weird that it should end with an adjective.
Okay. Thanks.
I have a question about the contextual embeddings for syntactic parsing. Would it be possible in the future to include them in the UDPipe so that the UDPipe will just process them without a complicated processed where I have to get the embedding somewhere and
yes, we are currently thinking about two ways to go to have. We cannot keep one model. That's because if we keep all the functionality that we use in the prototypes, then the models will get huge and no one will want to use them, and they will also not be very fast. So we are thinking two flavors. One of them would be full functionality, including the bird embeddings. Maybe we are not allowed to distribute the model itself, like the bird multilingual. But once you get downloaded this model, then everything should work. And the second flavor should be a small, nice, self-contained, fast one. And that's the big discussion, what should go in it and what should not go in it to keep it small and fast, with reasonable performance and accuracy trade-off.
Thank you.
Yeah, but it's a big problem. We want to also still keep it as a service, as a web service, and when we think about it, we need to have a server that serves bird embeddings or contextual embeddings, and that's very computationally expensive. We don't know if this will be in the web service. Maybe so.
I have a question back about the MRP task. So you said that with your system, the UCA got the worst results, actually, relatively speaking, so that the other systems were better for UCA. So
Yes.
do you have any idea why this was the case? You know, in which aspects
Yes.
the other systems were different and good
Yes.
for this phrase-based style of annotation?
Yes, so one thing which I said is the UCA style has a lot of layers, and our system is layered based, and the more layers, the more iterations you have to run, you lose information and it gets all tricky. So that's why I think we have, this is our worst performance. There are specialized parsers for all of these 5 frameworks, and some of the participants did just the same simple thing, that they used the the specialized system that is like based on syntactic parser for constituency trees for this one and one only. So I personally reviewed one paper where they used 5 separate models for each framework one. So maybe if we tuned our system to be a little bit different for UCA, we might get better results, but we honestly didn't want to, and secondly, we didn't have time because we all did it last time before the deadline. So we only had one system, and there has to be one of the frameworks in which is the worst, if we don't tune it to the specifics of the frameworks.
So one more sub-question. I should know that I know. The Harbin system, the winner, used also like 5 different systems, or was it combined in some?
I think the difference, I think they had one system, and the good thing was that they managed to model the transitions individually, not in a layered fashion. And I think that's where we lost most of our points, because we simply weren't technically able to program the sequence or to model the sequence of transitions. Even now, we were at the edge of, because TensorFlow 2.0, which allowed us to write all this architecture, was just freshly out, not just freshly now, but half a year or so. So we were very lucky that we could do it, but we were not able to write the sequence of the transformations individually, which we would like to do next year.
If not,